Let's discuss an example. Solve the recurrence relation. Solve recurrence relation Fn is equal to 3 times of Fn minus 1, where n is greater than or equal to 1 by using generating function. By using generating function. Now we have changed the statement. We want to solve the recurrence relation by using, and the condition is by using generating function. First step, we will have to find the generating function for this given recurrence relation. In the same manner, say we consider the given recurrence relation Fn is equal to 3 times Fn minus 1. It is the most important step for the generating function. Here the n varies from 1 and so on. We know the standard form of the generating function. Gz is equal to sigma. N varies from 0 to infinity. Fn Zn is equal to f0 plus f1z plus f2 z square f3 z cube plus so on. Consider number 2. Again the same step, multiply both sides of 1 by z raised to the power n. We get Fn into z raised to the power n is equal to 3 times Fn minus 1 into z raised to the power n. Then we select the value of the n from the given restrictions. We put n is equal to 1, 2, 3 and so on. From this we select the variation of n, 1, 2, 3 and so on, and sum up. Then this converts into sigma. N varies from 1 to infinity. Fn z raised to the power n is equal to 3 times sigma. N varies from 1 to infinity. Fn minus 1 into z raised to the power n. Take it number, you say 3. Again we can solve this equations simultaneously or by considering the different terms separately. Now, here we consider this sigma. N varies from 1 to infinity. Fn z raised to the power n. Start substituting value from 1. We will get f1 z plus f2 z square plus so on. We compare this term with the given generating function. Here it starts from f1z. It means from here. Which term is left? That is f0. Transfer it on the left hand side. Then we can write it gz minus f of 0. Then right hand side it is sigma. N varies from 1 to infinity. Fn minus 1 into z raised to the power n. Here this constant does not create any effect of a solution until or unless this constant is separately in addition or subtraction. Here we again put the value of the n. We get n is equal to 1. F0 z raised to the power 1, then n is equal to 2, f1 z raised to the power 2 plus so. No, we compare it with again the right hand side. We see it contains f0z, but here f0 is alone. It means we can take common z from this f0 plus f1z plus so on. No. Compare this right hand side bracket with the generating function this. It is complete. This is equal to gz. That we write z into gz. Now we compile all the condition by using number 3. It is g z minus f0 is equal to 3 times this constant will be shifted as it is because it is in multiplication into z into g z. Now, what is f0? In the starting, we take the value f0 is equal to 2. Say it is given in the statement. So we put this value here. f0 is equal to 2. This implies gz minus 2 is equal to 3 into z into gz. That is gz minus 3 times of z into gz is equal to 2. Take common generating function, that is 1 minus 3z is equal to 2. Let's see, gz is equal to 2 upon 1 minus 3z. This much we discussed in the previous sequence. It is the generating function. It is the generating function for the given recurrence relation. But now we are interested in finding the solution of the recurrence relation by using the generating function. Then we will have to proceed further from this step. For that, what we do, we can write it gz is equal to 2 into 1 minus 3z raised to the power minus 1. It is the alone factor. We can shift it up to the numerator by changing the power. No. This bracket we can solve it by using the binomial theorem like this. 1 plus x raised to the power n is equal to 1 plus x plus n into n minus 1 divided by 2 factorial into x square plus n minus 1 n minus 2 divided by 3 factorial into x cube plus so on. What is the difference between both? Here it is minus or here it is also minus. If we apply your take here in this way, 1 minus x raised to the power minus 1. This theorem will convert into 1 plus x square plus x cube plus so. We are concerned with this. Let's see here. We can solve it by using the binomial theorem. Here that is equal to 2 into 1 plus 3z. X is replaced by 3z plus 3z square plus 3z cube plus so on. That we have expanded this equation by using the binomial theorem. That is equal to, see, 2 into, see, it is also a sequence. If we represent, we say 1 is equal to 3z raised to the power 0, 3 raised to the power 0, 3z raised to the power 1, 3z raised to the power 2, 3z raised to the power 3. And we can write it in the summation form, sigma 3 raised to the power n into, or simply 3 into z raised to the power n. And n varies from 0 to infinity. Here we have started from 0. This one means 3z raised to the power 0. So we can write this sequence in this form: 2 into n varies from 0 to infinity, 3z raised to the power n. That is equal to 2 times sigma n varies from 0 to infinity, 3 raised to the power n into z raised to the power n. No. If we compare, it is gz. So what is gz? We know in the form of sigma n varies from 0 to infinity fn into z raised to the power n, 2 times sigma n varies from 0 to infinity 3 raised to the power n into z raised to the power n. Compare both sides. Compare both sides. Then we see sigma in front of sigma, then z raised to the power n in front of z raised to the power n. What are the remaining terms? That is fn is equal to 2 into 3 raised to the power n. It is a solution of the given recurrence relation by using the generating function. It is the generating function, and with this help we have found the solution for the given recurrence relation. Let us see more examples in it. The difference will come here. In the denominator we have single factor. If this factor increases, here see, if there are the two factors, then we can't transfer them to the numerator. Then how we deal with them? Let us see.